We're stepping into chapter 23 of Young and Friedman with a quick review. Before we can talk about voltage, we need to talk about your TPS reports. The work energy theorem. I'll remind you that when non-conservative forces, we'll label them NC, act on a system, the work done by those forces and I'll emphasize by these forces on the system. These words by and on are important when you're determining plus and minus signs. The work done is work, non-conservative. It changes the total mechanical energy E of your system. Total mechanical energy is the sum of kinetic plus potential energy. You could also split this up and talk about it as your change in kinetic energy plus your change in potential energy. And I'll remind you also, delta means final value minus initial value. So delta E is E final minus E initial. More often than not, we have a system that is only experiencing conservative forces, such as gravity or the electrostatic force in UP2, if only conservative forces act on a system. What's the non-conservative work done? Well, there aren't any forces that are non-conservative, so they can't do any work. This tells you when only conservative forces act on your system, your change in total mechanical energy is zero. Another way of saying this is total mechanical energy is conserved. Be very careful in this case, since delta E is zero, that implies delta K plus delta U is zero, which means that your change in kinetic energy is the negative of your change in potential energy. If I drop the pen from one height to a lower height, my delta U was negative, but my delta K was positive. I went from rest at a greater height to speeding up, higher kinetic energy. Delta K is positive when U decreased. So you have the negative of a negative change in potential energy giving you a positive change in kinetic energy. Then the work done by these conservative forces, we'll just use a label C, on a system is work conservative delta K, which is the negative change in potential energy. The final note here, the new aspect in UP2 is that the electrostatic force, QE, which we know and love by this point, is a conservative force. Along with gravity, it acts at a distance. It is not a contact force, and it will conserve total mechanical energy. We just saw the gravitational example where we drop a pen. The pen obtained a positive delta K by decreasing its potential energy. Gravity did positive work on the pen. If the gravitational force is my red pen here pointing down, the force is acting in the direction of motion. So your work integral from UP1, F dot dl, is a positive quantity. Positive work done by gravity implies a negative change in gravitational potential energy. The best analogy for voltage or electric potential is the gravitational potential. You may not have used this language in University Physics 1, but gravitational potential, if you leave off the word energy, has a defined meaning. It is defined as the gravitational potential energy per unit of mass. The best picture here to go with this idea is that a contour map, which has labeled continuous lines of constant elevation. Perhaps you're looking at the top of a mountain. Here's a line defining 10,000 feet above sea level, 9,000 feet, and 8,000 feet. These contours of elevation define something we could call the gravitational potential, capital V with a G subscript. Potential, just like potential energy, must have a definite reference point. In a contour map, you use sea level, and y could be your height above sea level. If we've previously expressed our potential energy for gravitational problems as mgy, again, y is your height above the reference, then the potential energy per unit of mass, you could pretend this is a test mass, similar to our test charge, little m0, divide out the mass, and you get an expression which is y times g, or height above sea level times the gravitational acceleration. Now, when you look at a map like this, we assume that g is the same everywhere on the surface of the Earth. Just keep in mind that the gravitational acceleration at the surface is calculated as capital G, the universal gravitational constant, times the mass of the Earth, divide by the radius of the Earth squared. This would give you 9.8 meters per second squared. And that value of G is truly dependent on your height away from the surface of the Earth. So as you climb a mountain, this radius gets a little bit bigger. It's like the radius of the Earth plus 10,000 feet. So the local gravitational acceleration on top of the mountain is slightly smaller than it is at sea level. But always bear in mind that the gravitational potential energy and this new concept we're calling the gravitational potential are not absolutely defined, meaning their values depend on the reference point. However, the changes in gravitational potential energy and changes in gravitational potential are absolutely defined between 2 points in space. And it is these changes, when you think back to the work-energy relationship, which will determine changes in changes in kinetic energy. Your delta U will be the negative of delta K. Enough about gravity. Let's get on to voltage. The word voltage is identical in meaning to electric potential. Be careful that you do not confuse electric potential with electric potential energy. Here we define the voltage as electric potential energy per unit charge instead of gravitational potential energy per unit mass, defining what we called gravitational potential. Here, electric potential is the potential energy per unit charge. It is a scalar field, just like the gravitational potential. It has a single value, V, at every point in space and time. It has to be specified with a reference point. The best example I can give you, without deriving the voltage of a point charge, we'll do that in our next video, I can simply state the voltage of a point charge is kq over r. We knew that the point charge creates an electric field, kq over r squared in magnitude, as you move away at a distance r. It points away from positive charges towards negative charges. Here, what you need to imagine is that we're looking at three-dimensional spherical equipotential surfaces. These are exactly like surfaces of gravitational potential that you could draw around the surface of the Earth as you go out into space. Now, the reference point, which is most convenient for voltage, will be to set the voltage 0 infinitely far away from your point charge, or from the region that you are interested in your problem. What are units of voltage? If we define voltage as potential energy per unit charge, then you're looking at units of energy, joules, divided by units of charge, coulombs. So the joule per coulomb is the SI unit of voltage, volts. This gives us an interesting alternate unit for the electric field magnitude. We have been using for several weeks now newtons per coulomb, because you think about how much force does an electric field place on a charge. Now you can think of how much does the voltage change per unit of distance, meters, that I travel in a region of space. So the electric field, say in the region between this 10 volt sphere and the 9 volt sphere, that electric field is greater in magnitude than it is out here, because you get a larger change in voltage per unit of distance traveled. As we move away from the point charge, the voltage spheres are going to spread out. Okay, voltage is going to fall off like 1 over r, and you'll find now that these electric field magnitudes are smaller because you have a smaller change in voltage over the same distance traveled. To add another rule for electric fields, we can state that electric field vectors must point from higher to lower voltage. By higher, be careful to understand that this could mean less negative voltage or more positive voltage. Lower voltage can mean more negative or less positive.